Good afternoon, ladies and gentlemen. I know that many of you have been here before and you know me, but we probably have a good number of people from the outside who are visiting the university for the first time. So for your information, I'm Nariman Farvardin, president of Stevens Institute of Technology. And it is a, thank you very much. It is a real pleasure to welcome all of you to the President's Distinguished Lecture. This is actually the 9th in the series of President's Distinguished Lectures. In almost all of these lectures, I have said it would be hard to top the previous lecture or the lecturer. These lectures have included luminaries such as Mr. Norm Augustine, the retired chairman and CEO of Lockheed Martin, Dr. Craig Barrett, former CEO of Intel, General Michael Hayden, I call him the Chief Intelligence Officer of the world, the former director of the CIA, Sharmin Mossavar Rahmani, the Chief Investment Officer of Goldman Sachs, Harold Varmus, Nobel laureate and former director of the NIH, among others. Today's lecture, however, continues to raise the bar even higher, and the reason is that we've invited a rock star, as you can see from the audience. For your information, we have a record response, a full house, an overflow room in the Babbio Center, watching the lecture through live streaming. I am indeed most honored to introduce Dr. Peter Norvig, Director of Research at Google. Dr. Norvig is commonly referred to as the not the guru, but the super guru of artificial intelligence. Dr. Norvig's very impressive and very extensive bio is actually in your programs, and therefore I will only recount a few highlights and interesting aspects of his truly illustrious career. Prior to assuming his current post, Dr. Norvig was head of Google's core search algorithm. So the search engine that you use probably many times every day can be directly attributed to his contributions many years ago. He also served as NASA's senior computer scientist at NASA's Ames's Computational Science Division. This service earned him the NASA Exceptional Achievement Award in 2001. Dr. Norvig co-taught an artificial intelligence class that enrolled 160,000 students. Now, for your information, I have been in the business of higher education for 34 years, and I think cumulatively, the total number of students I've taught doesn't exceed 3,000. So this is quite an achievement. When I grow up, I'd like to have a class that big. In fact, this course kicked off the current round of what is called massively open online classes, or MOOCs. Dr. Norvig's publications include the book Artificial Intelligence, A Modern Approach, which is considered the leading textbook in the field, and a number of seminal other works. He is also the author of the world's longest palindromic sentence. Do all of you know what a palindrome is? Yes? A palindrome is a sequence of letters or words or sentences or numbers or musical notes where reading the sequence forward is exactly the same as reading it backwards. And I was just having a conversation with Dr. Norvig. I told him that Joseph Haydn actually wrote one movement of one of his major symphonies as a palindrome. The third movement of his 47th symphony actually has two halves. The first half is exactly the backward version of the second half, but actually both halves sound very good to the human ear, which is quite an accomplishment. So if you'd like to talk to Dr. Norvig, and not about artificial intelligence and machine learning, but about palindromes, please find the time to talk to him during the reception. He is a fellow of the Association of the Advancement of Artificial Intelligence of the Association of Computing Machinery. He's a member of the California Academy of Science and the American Academy of Arts and Sciences. Dr. Norvig received the Bachelor of Science in Applied Mathematics from Brown University and the PhD degree in Computer Science from the University of California, Berkeley, where he has remained involved and serves on a number of advisory board capacities. As you can see from the slide which is on the screen, he will be talking today about creating software with machine learning, a fascinating topic, and he will talk about challenges and the promise. Please join me in welcoming Dr. Norvig.
Okay, thank you for the gracious welcome. Hello, everybody up in the cheap seats there. Hi. So we're going to talk about creating software, making stuff. And here's some typical makers of the early 20th century, and they made stuff like this. But then in the late 20th century, we started to get a new class of workers, and they made stuff like this that looks strange, and that's what it looked like back then. I actually was alive in those days. Now it looks more like this, but it hasn't changed all that much. And it's still hard work. It's just mental work rather than physical work. So what is the process? Well, we start off with a programmer, and they get an idea, and then they start to work through that idea and very carefully write down all the steps of how to do it. Under this condition, do this, and so on, and then you have a program that can do something useful. And that's traditional software development. But in recent years, and this goes back to the beginning of the computer industry, but has really taken off in recent years, we get people like this who've proposed a new way of making software. And this new way starts with a computer rather than with a human programmer. And it's the computer that's going to do most of the work. The computer is going to write the programs for us. How does it do that? Well, we still have a person with an idea on the side, but their idea is, here's a problem I want to solve, and the way I'm going to solve it is I'm going to feed the computer a bunch of examples, a bunch of data, and I'm going to tell the computer a little bit about how to process these examples. And then the computer is going to write the program for me from looking at those examples. But normally the computer doesn't write the program in the same form that a human was. Instead, we have different forms, and they look more like this, sort of a black box that you can't really understand very well. But at least I've shown the lid open a little bit that we can peek inside. And this is a program, so the computer is writing a program for another computer to run. We also call it a model. It's a model of the domain, a model of the examples that we've seen. And you all, many of you are engineering students, so you're all familiar with this, and some of you, way back in high school, you did this. You built these models, right? So you took a science class, you went out, you made some measurements, and then either using a ruler or using some calculator, you calculated the best fit to those data points, and that's a model. Once we have the model, we can formulate it mathematically, and then we can throw away the data points because the model is a complete summary of everything we knew from the data. And what can we do with that? Well, if we have a question, what would the value be for this point? And I've never seen this point before, then we can use the line or use the mathematical formula, and we can get the answer. So from some examples, we generalize to find the answer to an example we've never seen before. And that's really all there is to machine learning, is coming up with a model. And the general model we had in mind was it's going to be a line of some kind, gathering the data, fitting the data to say, here's the exact line that's the best fit for this data. And then now we've got a model, and now we can apply it to new cases. So all of machine learning is like that, and the complications are the models are a lot more complicated than individual lines. The data is a lot more complicated than a couple of points on a graph. And the algorithms for how you compute what's the best model given the data are also more complicated. So this is what the field is, and what's the promise for it? Well, there's two things. So first, it allows us to go fast. So instead of having the programmer sit down and days and weeks and months go by developing the program, you throw some data at the machine and you can instantly get a response. So you can do things much faster than you could ever do before. And secondly, as General Pattern knew, we can now change how we approach problems. So Pattern said, don't tell people how to do things, tell them what to do and let them surprise you with the results. So that's what the shift is. Rather than having the programmer say how to do it step by step, we're now telling the machine, I can't tell you how to do it. I may not even know how to do it. So say something like recognizing faces. I can recognize the faces of my friends and family, but I have no idea how I do it. It's in my subconscious. I couldn't, for the life of me, write down how to do it. But I do know how to train a computer to do that task by showing them examples. So we can do things that surprise us, things that we would never be able to do as a programmer, as well as just being able to move faster. So that's the promise. Now I want to show you some examples of how this works. We showed you the graphing the straight line, but let's do something more complex. So I'm going to look at the task that we call word sense disambiguation. And here's the task. I give you a sentence like this, and then I say, what sense of bank is that? Is that bank 1, the river bank, or bank 2, the money bank? And as a human, you can answer that pretty well. I want to teach a computer to do that. And the inputs that are going to be available is these dictionary definitions, exactly as they are, and a bunch of sample sentences that happen to contain the word. And from that, I want to build the program that I can now give it a sentence it's never seen before, and it will say bank 1 or bank 2. Now, if I think about how could I solve that problem, I say, this seems pretty complicated. When I solve that problem, I got to know the dictionary definition of all these words. I got to know how the syntax of English language works with noun phrases and verb phrases and all that stuff. And I have to know some facts about the world. I have to know what kinds of things are money banks and what kinds of things are river banks. And it seems like it would take me forever to do this. And if I did, now I've only done a word sense disambiguator for this one word bank. And now if I want to do all the other ambiguous words in English, that looks like a lot of work. And in every other language as well, I'm giving up. I can't do all that. I can't write all that stuff down. But could I possibly train a computer to do that? Okay, so let's think about how we could do that. I can't train the computer to know all these things about all the facts about what a bank is and how English language works. So I'm going to come up with the simplest possible model I can think of and just see if that model happens to be good enough. So here's the model. I take these dictionary definitions, and I get out my scissors, and I cut them up into individual words and put each of those words into a bag. And I do the same thing with the other definition. So now I have 2 bags of words, and here's the words that they contain. And by the way, there's a technical name for this model. It's called the bag of words model. And what this model says is in bag 1 contains all the stuff you need to know about sentences you could say with the riverbank, and bag 2 contains all the stuff you need to know about sentences you could say with a money bank. And this model claims that the way an English sentence is constructed is not by somebody thinking in their head about all the meanings and the dictionary definitions and the noun phrases and the verb phrases. The way we construct a sentence is we reach into the bag and we pull out words and we put them next to each other until we're tired of pulling out words. Now, that sounds like a terrible model of how English works, right? It doesn't work like that. It's much more complicated. And the statistician George Box said, well, it's not so bad. All models are wrong anyways, and some of them are useful. So don't worry so much that that model is a terrible model. Ask, is it useful? Okay, so is it? Let's try. So I got these 2 models. These 2 bags are seeded only with the words I got from the dictionary definition. And now I'm going to take all those sentences. And the sentences didn't say which was bank 1 or bank 2, but they're still going to be useful to me. So even though the sentences didn't have the right answer, I can still use them to improve my model. How do I do that? So I take the first sentence, and I look at each of the words, and some of the words don't appear in either bag, and some of them appear in one bag. So the one in blue, the loans, occurs in bag number 2, And some of them occur in both bags. The word the occurs pretty evenly across both bags. So I do that, and then I do a little bit of sort of counting up and say, which bag is that sentence most likely to have come from? What's the probability that if I picked randomly from bag 1, I would create that sentence, versus if I picked randomly from bag 2, I would create that sentence? And the answer is it's more likely to have come from bag 2, because that's the bag that contains the word loaned. So now I've made a prediction. In this case, the prediction happened to be right. But more importantly, I'm now ready to upgrade my model. And I take all those words and I throw them into bag 2. And now bag 2 is a better model of what it means to talk about a money bank. And I keep on doing that for thousands or millions of words. And pretty soon I got big bags, but they're more effective at this task of disambiguating words. And so you start getting bags with counts like this of lots and lots of words, and you realize that everything I need to know about machine learning, I got on Sesame Street. All it is counting. We're building this model by counting up how many times this word was relevant to sense 1 or sense 2, and now I can apply it. Now I can take sentences I've never seen before and score them, and some of the times I'll get the right answer. Occasionally I'll get the wrong answer. That's okay. Let's see how well I do. So here's a graph, and I've trained it on 1 million words of these sentences that have bank in it. And there's 4 bars here because there's 4 details of slightly different algorithms for how you count and how many points you get for having the word or not, and so on. And we get 80 to 85% correct. Now, in the old days, like 10 years ago, if you were an academic, what you would do is you would say, well, the best one of those got 85%, but I'm going to be very clever, and I'm going to invent a new algorithm, a new way of scoring, and I'm going to try to get to 86%. And if I do, then I can publish a paper about it. And people play that game. That's why there's 4 of them there, is because somebody did one, and then 3 other people came along and said, no, I can do better. But what we soon realized is arguing over that, trying to come up with a better way, is less effective than just saying, well, that was 1 million words of data. I can go back out on the web, and I can easily get up to 10 million words. And look, boy, that's a big difference. And 10 million words, that's not so much. I can get 100 million words, or I can go out to 1 billion words. And I'm going up, and the differences between these algorithms that we used to think it was so significant, whether you used algorithm 1 or algorithm 2, those differences are small, but the difference from having more data tends to be big. And now it looks like we're pretty much asymptoting out. So if I kept going, I'd probably get diminishing returns. And so the best I can do is probably somewhere around 95, 97% correct. But that's pretty good, considering the only work I did was to go out and gather up words and throw them into bags. And the phenomenon here of saying, here's an application where if you have a small amount of data, tens or thousands of words, you don't do very well. But if you have a lot, millions or billions, you do really well. That's this notion of this data threshold where you pass over from doing poorly to doing well. And you could say that companies like Google are built on looking for curves that look like this and saying, can I find problems for which I can do much better if I have a lot of data? So that was one task. Now I want to move on to another task, or actually a whole field with a collection of tasks, a field of computer vision. And why is that useful? Well, you can use it as one of the components of a self-driving car to figure out where the pedestrians and other cars are so you can drive safely. You can do things like this as an application of Google Translate, where you point your phone at a sign in another language, and it translates the sign and puts the text in the right font right into the image on your phone. And for me, as an amateur photographer, I spent a lot of time in the past organizing my photos and attaching keywords to them and putting them into folders and reorganizing them when I felt I made a mistake. And then Google Photos came out with this ability to do that automatically. So I said, let's try it. I'll strip all the keywords off all my photos. I'll throw them all in and see what happens. This is where I get an advantage, right? You guys don't get to show me any of your baby pictures or travel pictures, but I get to show them to you because it's part of the presentation, right? And so you come out like this, and it's got categories, and the categories are pretty good, and if we click into the categories, it's done the right job. It's put everything in the right category. And beyond the categories, I can search for things. So birds was a category. I can search for pelicans, and I get them. And flowers was a category. I could search for clematis, and oops, I only got 4 out of 5, right? So the top right one, that's not actually a clematis. So it's not perfect, but it's doing a really good job. And beyond just doing binary classification of is this in the category or is it not, it also is doing graded classification. So if you ask for a keyword, it'll show you the best examples. So I ask for nose, and I get a bunch of really prominent noses, even though I have lots and lots of other pictures that happen to have noses in them. Okay, so that's pretty transformative, that all this can be done, these millions of categories, all done automatically, just by looking at examples and having some clever work of dealing with them. Now, I want to give you some idea of how this type of stuff is done, but there's a cliche that every time you show a math formula, you lose half the audience, and I'd have to show so many formulas that we'd be out of audience members. So I won't do that. Instead, I'll use an analogy. So here's the analogy. Suppose you run a company that sells these kind of tile displays, and you have a catalog where people can order, this looks like a nice scene of Tuscany or something like that, and you got a catalog with a bunch of different tiles, and people can go for them. But then you say, you know what, this is the internet economy, so we should have something where people can upload their own picture, and then we'll make the tiles and ship them out to them. And it turns out that's really popular, but there's a problem, that making custom tiles one at a time is really expensive. So you're not making a lot of profit on this. So you get the idea that what we should do is we should have an inventory of tiles. And then when people upload their picture, we should go into that inventory, get out the tiles that could be pieced together to make their picture and ship that out to them. And then the question is, what tiles, what little pieces should you put into inventory? Right? So that's the question. And how do you answer that? Well, one way to say is, what pictures am I going to get in the future? And that's probably representative of pictures I've seen in the past. So take pictures that people have already had or wherever you can find them, get a bunch of pictures, and then there's some fancy math that I'm going to omit here, which says, out of all those pictures, what are the most important pieces, right? So, like, you probably want to have a piece that was all blue because there's a lot of sky and a lot of ocean, and you need some blue for that. And it doesn't matter if it's exactly the right shade, because we're allowed to be a little bit off. And you'd probably want some noses and eyes and faces, because lots of pictures have people in them, and so on. And so I'm just speaking off the top of my head, but there is a mathematically precise answer to what are the component pieces that best make up all the pictures in this collection. And so that was tried. Bruno Olsheisen at Berkeley was one of the first to try it, and he did it, and then he looked at the results. It was very exciting to see. And what did he see? This is like the primitive set of all things that can make up all pictures. And what he discovered is pictures are made out of lines. So that's kind of disappointing, right? And it's true, but we already knew that in kindergarten when they first handed us a pencil or a crayon. We knew you can make anything out of straight lines. And here there's some that are horizontal, some that are diagonal, some that are diagonal the other way. So this was a true result, but not a useful one. But we didn't give up there. And the field as a whole said, well, maybe the problem is we're only asking for components at the lowest level. What if we had 3 levels of inventory? And so the lines make up small pieces, and then those can make up bigger pieces, and those can make up bigger pieces still. And that was the transformative step. And that happened, I guess, around 2012. There's some precursors before that. And it actually worked. So when you do that, at the first level, you still get the lines, but at the next level, you get things like eyes and noses, and at the next level, you get things like faces, right? So this system automatically said, a face is an important thing, and I'm going to allocate some of my inventory to that. And we've gone on from there. We build systems now, not with just 3 levels, but like with 20 or more levels, and there's lots of complications to it. But it all comes down to saying, find the most important pieces, combine them together, and now when you get something new, you can choose from that inventory to create a new one. And what can you do with that? Well, so I want to show another example, and we've shown a little bit of language stuff, and we've shown a little bit of computer vision stuff. One of the tasks is to put those two together. So here's the task of caption creation. So given a picture, can you make a caption for it? So here's a picture, and we asked a human to come up with a caption for it. And they said 3 different types of pizza on top of a stove. Then we trained a system by showing it lots and lots of pictures and corresponding captions, and it learned a model of how to go from picture to caption. And then we showed it this picture, and it came up with 2 pizzas sitting on top of a stovetop oven. And that's pretty good, because you have to look really carefully to see that on the left there's a tomato and looks like a spinach or a pesto or something. So it's doing a good job. And I could go on like that, but it's no fun to show the good jobs. So let's show some of the mistakes, both because they're fun and because it gives you some idea of where this type of system breaks down. So here's a rather unusual picture. And the caption it came up with is a couple of giraffes standing next to each other. So the system had no experience with horses in purple pajamas. But if you look at the pattern on the pajamas, it looks a little bit like the reticulated giraffe pattern. I don't know why it came up with a couple rather than one. And that's part of the problem with these systems, is that they make mistakes. It's hard to understand what the mistakes are from. Here's another one. A reflection of a dog in a side view mirror. Objects in mirror may be larger than they appear. And I guess here, dogs are just a lot more common than elephants. Didn't have any experience with elephants in mirrors. Here's one. A man riding a skateboard. And I don't know if you can see it from the back, but there is horizontal marks in the floorboards there that look maybe a little bit like the deck of a skateboard. There aren't any wheels on the skateboard. But the system just somehow imagined that nobody, not even the king, could be in that position unless they were balancing on a skateboard. Okay, so this is the promise. We can do amazing things. It's not quite perfect. But what are some of the challenges? So we said we could go really fast, and that's great. But sometimes when you go fast, things happen. So what do we have to watch out for? Now, one of the fascinating things that's come up in the last few years is this notion of adversaries. So I could do pretty good on most queries. When I did the disambiguation, I got up to 97%. But what if there's somebody out there who's specifically giving me an example that's especially hard for my program? It understands what my program is doing, and it's trying to actively defeat it rather than just observing nature. So here what I have is schematically the decision boundary of pictures, and all the pictures on one side are labeled as pandas, and all the pictures on the other side are labeled as gibbons, and so it's done a pretty good job of that. You can see there's a couple of red and green that are across the wrong side, so that means those are ones that it got wrong, but mostly it gets them all right. But now I can ask, what if I took this picture of a panda, and that dot represents this place in space where that picture occurs, and what if I just moved it ever so slightly until it went over the boundary and into gibbon territory? Okay, and I can do that because I have an understanding of my model, and I can do some math, and I can ask what's the minimum number of pixels that I have to just tweak a little bit in order to shift it over and make the computer give the wrong answer. Or is it even the wrong answer, right? So here's the picture of the panda. Here's the computation of how much I have to move each of the pixels in each direction. So some of the pixels get a little bit more red, some get a little bit more blue. And this 0.007 here means I'm adding mostly panda and only 0.7% of the little bit of shift. So it's a very small shift. And what do I get? Is the picture going to look like a half panda, half gibbon? that's slightly more gibbon, what is it going to look like? What do you think? Well, the answer is, it not only looks like a panda, it looks like the exact same picture, right? So I've made this change, which totally fooled my program, but has absolutely no effect on fooling your visual system. So clearly, the program is doing something very different than you are. And by looking at kind of the fuzziness of that, the noise we added in the middle, it seems like it has something to do with very high frequency changes that your visual system just doesn't detect. So the aggregate accuracy overall might be very good, but it's making some really bizarre mistakes, and we want to understand that. And this really changed my way of thinking about things, where I used to think that we had divided up the world pretty well, and maybe around the boundaries between two different types of image, we would make some small mistakes. But now I think it's not like that at all. Now I think there's these very narrow corridors that we get right, and in between them, we have no idea whatsoever. That there's just zillions and zillions of possible pictures, and most of them we have no idea. And the only reason we get a lot right statistically is because everybody takes almost exactly the same picture. So there's a problem in debuggability and explainability. So if I take a traditional program and it has a bug in it, there are techniques I can use, and I can say, aha, I know that the bug must be in this module right here, because coming into it, everything was good, and coming out of it, things were bad, and so therefore I've isolated the bug, has to be here. But with a machine learned system, it's just not like that. There is no one place where you can say everything was good flowing in and it was bad flowing out. Rather, everything affects everything out. So we can't debug it, we can't change it, and we can't really ask it to explain itself. And there's a lot of work going on to make that better, but we haven't got there yet. There's also a lot of issues around privacy, security, and fairness. So privacy. If we're going to base systems on data, and data is valuable, then it'd be nice if we could collect data from lots of people, but we don't want that data to leak out. We want your data to be secure. And there are some nice systems for being able to train multiple systems, aggregate them together in a way that you can never get out individuals' data. But that's a continuing research field. Fairness as well is a big issue, where we have to say, what is it that we really want? And are we achieving that properly? Right? So I said we've changed the way we program from saying, this is how we're going to do something step by step, to just saying, hey, here's some examples, and here's what I'm telling you you're trying to achieve. But that puts a lot more emphasis on this decision for what is it that we're trying to achieve. So let's give you an example. Let's say I'm doing a speech recognition system, and I achieve a certain level of accuracy, and I want to increase that. So I'm asking, what's my measure? Where am I at now? And I say my measure is total number of correct recognitions of words over all my users. And say I'm at 95%, and I want to get to 96%. Now, say I come up with an idea that says, hey, we've been trying to optimize across all our users, but if we split the users up into groups, depending on the way they speak, and then maybe I could optimize one of those groups at a time, and I could increase those. And we'd say, great, that sounds like it'll work. Now, if I'm going to do that, and I have a limited amount of engineering resources, and there's 5 or 10 different groups of speakers, who am I going to work on? Will I work on the large group with millions of people, or I work on the small group with only thousands of people? Well, if my goal is to increase the overall score, then I got to work on the big group, because now I'll get a big return for a small amount of work. And so that means, without me having any ill intentions, I've said, my system is encouraging me to help the majority group get richer and the minority group get poorer. And this, for speech recognition, this group could have to do with the shape of their larynx or something like that. And in other applications, it could have to do with other demographic type factors. And if we're okay with that, if we're okay with saying the people who speak in this kind of voice will do better, and we don't have time to improve it for these small minority group speakers, then that's what we'll get. If we think that's not fair, then we have to change our objective. Then we have to say, you know, I thought I was trying to optimize over everybody, over the average, over all people, but instead maybe I want to optimize over each group individually. Maybe optimize over the score per group rather than the score per person. And then I have to decide which groups are worthy of that kind of protection and which groups aren't. So, you know, right-handers versus left-handers, does that count? People are wearing blue shirts versus purple shirts, does that count? Or what groups are deserving of fair treatment and which groups were just sort of contingent and we don't have to worry about? So that's a big question to deal with. And finally, there's this problem of the sands of time, or a change. We call it nonstationarity, which is just a fancy word. And it means that we train these systems with data that we have, but the world doesn't stop. And the world goes on, and new data is out there, and the world changes. And so a system that was trained to do one thing can degrade very easily over time as circumstances change. And now we have a whole new problem in saying, how are we going to deal with that? Are we going to update the system continuously? If we do that, are we going to lose old wisdom? Do we keep stuff from exactly 1 year ago because, you know, everything is different during the Christmas holiday and we don't want to forget what we did last Christmas, but in the winter we can forget what we did in the summer? How do we deal with that? And how do we make systems that are secure and safe and verifiable? Because we built a whole software engineering system on the idea of we release new systems. And it used to be software companies would release only once a year, you got a new update. Now it's much more frequent because we can distribute over the web rather than by putting things in boxes and shipping them out. But we're not yet to the point where we can reliably say we're going to have a new update every second as new data comes in. We don't have the systems in place to do that kind of reliability. So these are the types of issues that we're dealing with, and I see a lot of promise. I also see a lot of challenges. It's exciting to work on these challenges, and there's a lot of opportunities. So why don't I throw it open for questions?
Is there anything that is related to cluster theory in this? Because one of the software developers that I've come across is Ringtail, and they have actually set up clusters of balloon-sized spheres that are smaller and larger, and they apparently give you an idea of how to conceptualize the review of data.
Okay. All right, so I don't know that particular one, but a couple things to say. One is that certainly the visualization is another big challenge for us. And that I think we're better at making decisions. Say, here's a model, I'm going to run it. It's going to say, this is a gibbon, this is a panda. And we're not as good at doing visualization to give us understanding of, well, why is this a panda? Or what makes this an unusual panda? Or tell me about all the animals and how they relate to each other. And so tools like what you were describing, having some way of summarizing large amounts of data, that seems like a very useful thing. Then the other thing I got out of your question is well, first of all, you're exactly right that this idea of predictive coding is very important, and that another way, another metaphor for what machine learning is compression. That if you can take data and compress it, it means that you've understood the true meaning of it and you've kept the true part and threw out the contingent part. And so all machine learning is, in a sense, compression. But you were asking about clustering, and that's certainly an important thing. And we distinguish three types of machine learning. So we do clustering for unsupervised learning, where we throw a lot of data in and ask the system to make sense of it. And that was the first step of the Google Photos application of just say, which pictures go together? Let's put together the ones that are similar and do that, and we can do it in a hierarchical form. So these are similar, but then they're grouped into a larger group, which is grouped into a larger group. And so we call that unsupervised because we're not giving you the answer. The programmer of a machine learning system is a teacher. In this case, the teacher isn't giving you any answers. They're giving you the unworked problems and letting the system figure it out. We also have supervised learning, where we give you a problem and the answer, as teachers often do. And that would be the second part of the Google Photos application, where we say, here's the right answer. Here's a label that corresponds to this picture. And so you had these guys all clustered together, and now I'll tell you what the right label is for that cluster. And then we have a third type of teaching, where we call reinforcement learning, where the teacher doesn't say what the right answer is, but just gives you some indication of whether you're doing well or doing poorly. And that's used in things like game playing, where we play chess or we play Go. It's really hard, unless you're a super expert, to say that was the right move or this is a good position. But it's really easy to play a game to the end and say, I won or I lost. And so that winning or losing, that's a reinforcement. If you get one reinforcement for a game that had 50 moves, you're not quite sure which move was, I lost the game, which move was a mistake. I can't really tell with just one. But once I played millions of games, then I can start to zero in on that. And those reinforcements can guide me towards the right answers.
Why do we need humans anymore? A number of major scientists are now threatened by all the artificial intelligence that's going on. So apparently they think, or some people think, that these new forms are becoming superior to humans, and are we going to need humans anymore?
Right. Well, first of all, we like humans, so that's a good enough reason. Secondly, we're in charge still, right? So we're building tools, and we build these tools to serve us. And to the extent that they're useful, we use them. And to the extent that they free up time for us to do other things, it means we can do other things. So that's one answer. And then the other answer is we're not yet at the point where they can do it all by themselves. So everywhere here, there was a human in the loop saying, here's the problem I want to solve. Here's the outlines of a model. I don't know all the details of the model, but I can say in the abstract, here's the model. Here's the data I've collected. And here's the learning algorithm I want you to apply. Now, the human does all that. Then the machine takes over and does a lot of work and comes up, fills in the parameters for the model. But there's still a lot of place for the human to be. Humans are much more flexible and adaptable for kind of one-shot problems. Where if I was going to do the same thing a million times, I probably want to build a computer system and take the human out of the loop altogether. But if I'm doing a different thing every day, the humans are going to be much more flexible, and we're still going to want them there doing that. And I guess we see a lot of cases where you want to have a combination of humans and computer tools to help them. So you see that in things like business analysis or security analysis, homeland security type things, where they say, let's team the best computers we have, the best analyst who's an expert in the domain, and the best nerd who's an expert in using the tools. And between the three of them, then you get something that's more powerful than if any one of those was missing.
Dr. Norvig?
Yeah.
I'm curious about your thoughts about the legal liability when you can't exactly see into the black box as you describe it, and you try to correct for most of the problems, and maybe areas like safety, self-driving cars, et cetera. Have you guys thought a lot about that?
Yeah, so certainly it's a huge issue. We're thinking about that. And some of the issues are new to machine learned systems. Some of them are not, right? So, if we built software by hand, by programmers thinking about it, well, if they did it right, then there would never be a bug, right? But we know that there always are bugs, because we can't, humans are fallible, we can't think ahead, we can't think of all possibilities. So all software is going to have bugs of some kind. And the question here is, well, the bugs are going to be slightly different than the types of bugs that a human would put in. A computer system is going to put in different types of bugs. So one question is it a legal defense to say, well, I did much better than any human could possibly do? My level of bugs were much smaller, it was much safer, more secure, but in this one person's case, yeah, I admit we did something wrong. Now, to what extent are you liable under those circumstances? And I'm not sure how the legal system addresses that. A lot of it has to do with showing that you've done your due diligence, that you've done everything that was possible, right? So if I build a bridge that falls down or a boat that sinks, then as an engineer, there's going to be an investigation, and if it shows I was negligent in some way, then I'm liable. But if it shows, I did everything up to state of the art, then I'm probably not liable. And so I think it'll be the same thing with machine learned systems. But I think we are behind, that we got ahead in the raw capabilities because people were just striving to get higher accuracy, and we didn't think as much about all the other properties other than just accuracy of saying reliability, explainability, understandability, and so on. And we're trying to catch up in those areas.
What is your feeling regarding generalized human intelligence for the future? And is the move into machine learning due to a failure of generalized human intelligence research?
So you mean generalized AI?
Creating a human with emotions and all the faults and benefits or abilities of humans.
So I guess a couple of things. One is we don't know how to do that. Well, actually we do. So my wife and I created two humans. I got to admit, she did a lot more of the work than I did. So we can do it the good old-fashioned way, but in terms of the engineering way, we don't know, right? So it's still a mystery. I think we're making pretty good advances in terms of neuroscience and so on, of understanding things better, but we're still a long ways. Now, if we did understand that, then the question is, do you really want to build a human? Why settle for that, right? So if I'm going to build a calculator, I don't want to build a human calculator that's going to get 1 out of 20 multiplications wrong. I want to build a superhuman calculator that will get everyone exactly right and can do it 1,000,000 times faster. And same thing for all these other applications, right? So I want to build a machine translation system that can translate between every pair of 100 by 100 languages, and no human can do that. All right, so I want to aim for superhuman performance, and in doing that, we're narrowed down to certain tasks. It would also be good to get all this emotion type thing, right? So think of that as a separate task, right? So I want something that's at human level, or maybe even superhuman level, at interacting with other humans. That hasn't been a big research area in the past. I think it's starting to be, as we're moving from interacting with our computers by punching buttons to talking to them. And so you have your Google or your Siri or your Alexa that you're now having conversations with. And today, those conversations are pretty stilted. You can't say very much. But over time, that will get better. And there will come a point where getting the emotions right will be the bottleneck in that. And then we'll start really have a science of getting that right. But I'm still not sure that you want to have something that looks and feels exactly like a human. I think you want something that gets you, that understands you, but you also want it to have these superhuman powers to remember everything rather than just remember as much as a human can.
Maybe an interesting point to make a segue. What happens when my robot or my artificial intelligence and your artificial intelligence collide because you have different value systems?
Yeah.
And that could be as simple as we drive on the right side of the road and you drive on the left. On the other hand, it could be, I think this is good and you think it's bad. What happens when we start winding up with artificial intelligence that has to deal with that?
Yeah, that's a great question. I'm not so sure if adding the artificial intelligence changes that so much, right? So we've already have humans, individuals and nations and corporations that already have exactly these problems, and we see what happens when they bump up against each other. And so computers will have to play in that same environment, and there will be issues of I want one thing and you want another thing. Stuff like what side of the road to drive on, that's pretty easy to accommodate because we can both agree that if we came up with the same answer, that'd be better for both of us. And so that's a stable equilibrium to get that right. But other things we can't agree on, right? And we brought up the question of some of these critics saying, well, what if an artificial intelligence system has values that are slightly different from a human's, then wouldn't that be terrible? Wouldn't it lead us off in the wrong direction? And the answer is, well, there is no such thing as an individual human value. Humans have lots of different values, right? And we can't agree. We can't even agree who can go to what bathroom. How are we going to agree on these bigger societal issues? And so there's going to be lots of differences between humans, and there'll be lots of differences between machines, and we'll still have the same kinds of battles that we had before. I'm not sure having machines changes it that much.
Will that be the next big resolution area?
Yeah. I don't know. Hard to predict, especially the future.
Appreciate your comments on jobs. Google, in the last 4 to 6 months, has gotten heavily involved in looking at machine learning and how we look at jobs from the candidate point of view. But downstream, we're also going to see how employers are going to be using machine learning in terms of that selection and assessment. I can see a lot of challenges, but I'd be curious as to the ones that you see.
So by jobs, you mean the job hiring process? Yeah. So it's an interesting application, right? And we had some discussions earlier about how you do that for the college application process as well. And the applications and acceptance and scholarships and everything else that you want to make the right decisions. And you want to know if you make an offer to this person, is that going to work out well? Are they going to turn you down? Are they going to go someplace else? Are they going to be helpful and productive member of society, or are they going to be a pain who makes things worse? And you have very limited amount of information. And so I think there is an opportunity to look at the available data and have machine learning as a tool that helps you in this process. I think you're probably best off to continue what we were talking about before, have this be teamwork, get the machine making its recommendation, get the expert admissions people working on it as well, and get the nerds to translate between the two. I think there is an opportunity to improve the process by getting around some of these implicit biases, right? So everybody has biases, they come up at the strangest time. Sometimes they come up because of societal issues of, I just sort of implicitly don't like one group over another. And sometimes they come up for very incidental individual type things of, oh yeah, we should accept this candidate and they'll be great because their voice sounds just like this other person who was great. And actually, the sound of their voice has nothing to do with their performance on the job. But we, as humans, we can't help but be pattern matchers, and we see a pattern that matches, and we apply it, and we overgeneralize. And I think using machine learning can maybe help you at least be aware of those types of biases and measure them out.
We know from history there's been technological progress where it's brought us a lot of advantages. I mean, a lot of electrification and steam engines, and invariably that's improved our lives and really disrupted societies. So I mean, I'm wondering if this paradigm change with machine learning and having computers and algorithms learn from examples, that they would learn, what they would learn are more of the biases that are inherent in the human condition, and would just reinforce that, but not like other tools, but really with a lot more firepower, so that our ability to correct those things, to make those adjustments, can't keep up with the pace that the automated decisions are being made. So, my question is like, what guidance would you give us in terms of trying to, maybe putting in place institutions or some kind of framework for trying to decide between where to make the value judgments where the humans need to intercede or maybe to slow down, and that sort of thing.
Yeah, so I think that's a great question, or it's more than a question, it's a whole topic area. And I think that's exactly right. And that's what I was trying to get at with the metaphor of the race cars of, technology allows us to go fast, but if we go fast, sometimes we crash in ways that we wouldn't have if we were going slower. And you raise this great point of garbage in, garbage out. So if society has certain prejudices and we train our system on society, then we're probably going to learn those. And we have to work especially hard to get around that. And we can do that in several ways. So we can curate the data up front to say, well, I'm going to just take everything, right? Believe it or not, not everything on the internet is true. And not everything is fair, and not everything is something that you would want to learn. And so we can put in place systems to try to get the high quality stuff without the bias in it at the start. So that's one thing. That's never going to be perfect. Some of it will still slip through. And then you can, at the back end, you can put other processes in place to say, let's not just accept a decision because this computer said so. Let's look more carefully at it, and let's have other processes in place that check those decisions. So maybe it's difficult to avoid all biases in one program, but maybe it's easier to write another program that will detect bias in the processes of another. And now you've got to adjudicate that. We see examples of things like that happening, and we have to complicate our decision processes. We have to be careful up front about, we talked before about what is it that we really want, what are we trying to optimize. And I think you're certainly right that sometimes we may choose not to go as fast as we can, to say this is not sustainable to go at this pace, right? And I think it's good that we're starting to have these conversations now as things are getting started, right? So as you point out, you mentioned electrification. I think like the automobile would be another good example where internal combustion engines have done a lot of good, but if 100 years ago somebody had been saying, hey, let's worry a little bit about pollution and maybe worry about the structure of our cities and what taking up everything with asphalt is going to do to that, maybe we could have arrived at a better place now if we were worrying about that from the start rather than reacting to it afterwards.
The thing is, I want to develop a system that can understand human intentions. Basically, in every country, if you see, people are more focusing on security. Like, they just want to make their environment safe, their city safe, or any organization safe. But if you look at people, or if people who commit crimes, they are doing with an intention because they do not have money, or they do not have those opportunities, or they do not have jobs. So how can we use machine learning to detect a person's intention, a good or a bad intention? Or suppose if a person is a criminal, there are many people behind bars in prisons who regret that they have done something. There are people who feel guilty. And we all know that you go to any company, even an institute, that person or the head will not employ you or wouldn't even accept you as a student to study. So their entire life goes like it's a waste. So how can we create a system so that you can solve this unemployment gap and it can create a difference in the world? So like, how can we use machine learning for that?
Yeah. I don't know if that's really a machine learning problem. I think, again, this is mostly a societal problem. I think there are ways for information technology to help. And I know, like in California, we had this proposition, I think it was Proposition 47, which said if you've been convicted of a certain class of crimes, like you passed a bad check or something, that you can get that taken off your record, and that'll make it easier for you to get a job, get a loan, get all these other things. But because this was done by legislatures, it's like the forms to fill it out were like 20 pages long, and the office where you could do it was open from 9 to 11 on Tuesdays only. And so nobody signed up to do it. So there's a nonprofit called Code for America, and they hire programmers. I don't think they have that much in terms of machine learning, but they built a little phone app that walks you through the application process, texts you when it's your time to have an appointment, reminds you to do all these things. And now they've increased the completion rate something like tenfold over what it was before. And so I think there is a lot of opportunities to use technology for things like that to help people get back on track.
So I've been reading a lot about stream analytics, and I realized that machine learning is an integral part of it. If you want to train the model, you have to train it, and stream analytics doesn't fit it completely. Like, there are a lot of complications involved in this area. So what is your take on this, for machine learning in stream analytics?
It's not exactly an area I cover, but I think this idea of dealing with changes over time is an important one. The explosion of techniques we've had in recent years first started with more static things. So you look at a picture and it's all there at the same time. It doesn't evolve, doesn't stream over time. But there have been add-ons to that. We have this thing called long short-term memory that keeps track of what's happening recently and also a little bit of what's happening long-term. And that allows us to develop systems that progress over time. So I think that's important. I think there's still a long way to go there. That's still very kind of literal, one step at a time. It's hard to use systems like that to, say, represent concepts like every other Tuesday. So it's sort of executing time without really understanding time.
So the solution's still existing. They're still using buffering as one of their concepts to understand the model and run through it. So we can say there is still a lot of development which requires in this particular area, if that's true.
Yeah, I think that's right. And I think everything's changing, and it all depends on who gets excited about what problems and puts some time into it. So if you're up for it, you can help push the field in the right direction.
Thank you so much.
Yeah.
As much as I'd love to pick your brain on the nitty-gritty methodologies for machine learning, that might be a bit boring for the rest of the audience. I have a question about control. If you have a generalized intelligent actor, how would you give it a goal while keeping it apathetic to being turned off if something goes wrong?
So this is the argument that maybe we'll lose controls over our systems because they'll want to live forever. And so far we haven't had that problem because we haven't gotten to the point where we have systems that have goals like that. I'm not convinced that a system would have such a goal, because I think that we want to preserve our life because of the way we live, that we get one shot and when we're turned off, that's it. But programs are different. They can be turned off and turned back on again. They can be duplicated 1 million times and run in 1 million places. They can be modified and run some more, and we don't have any of that. So to try to impose on a form that's so different from what we are, our perceptions of life and preservation, I think that doesn't make too much sense. But we don't know what's going to happen, right? And so I think a big part of it is we need better languages for communicating with these systems. So we want to be able to say, do this. We have to phrase that in a way that makes sense, that the system can understand, and when it can know when it's the right thing to disobey with us, right? So we tell it, here's our policies, here's what we want you to do, and then it may say, but now I'm in a contradiction. And I have to break one of your rules because you told me things that were inconsistent and I have to break it in some way. Or you told me a thing in the past, but I think that no longer applies. And we've had that problem in society as a whole, right? So we program society, we program like countries with laws, And in the US, we had a bug in our Constitution, and Abraham Lincoln got assigned the bug fix to fix voting rights, and it was a very expensive bug fix in terms of human rights, but eventually he got it right. Now, how do we tell a system like that? So say we had built a computer system to run our government, and we said, here's our rules for who gets to vote and who's a citizen, and now we said, well, I want to change that. Is the system going to say, okay, let's change it, or is it going to say, no, you can't, because that violates the rules that you already told me? There's a contradiction. And so we need systems to be able to describe what's allowed to change and what isn't. And there's been some nice work on that of figuring out what the priorities are, figuring out what the language is for describing these goals and so on. I think there's another problem of we don't really know what we want, right? So we can't tell the system. We could say, so either we lie about what we want, right? So you ask people, what do you like to eat? And they all say, oh yeah, I eat healthy food all the time. And then they sneak out and have that double hot fudge sundae, right? So we lie about what we want, and sometimes we don't even know ourselves what we want. So there's been a lot of talk about having computers observe us to try to understand what it is that we should want. I think that's promising. I think there's still issues with that, right? So if a computer watched me play chess, it should say, oh, I see what the goal of this game is. It's to last about 10 or 20 moves in and then make a terrible mistake and lose. Because that's what he does every time. So we have to figure out ways that computer systems have to learn our better angels and not our worst forces, and distinguish between them. And that's a great research topic too. You should work on that one.
I was wondering, it seems based off of your presentation that you were able to analyze sentences and then pictures with computers. A logical progression kind of seems like analyzing video with that.
Yeah.
Is Google currently doing that? And if so, how would you analyze video and kind of sort it?
So that's certainly true, and I think that's a great thing, and I think having video, I'm hoping, will be a big advance. There's a problem with text and photos, which is they only capture things that were sort of very explicit, right? So you only write about things that you think are worth writing about. And so a lot of things that are so common and obvious you don't bother writing about. And you only take pictures of things when you think it's important. Well, nowadays with smartphones, that's less true. But you're still getting a biased view of the world. And that's still true with video, but I think video captures a lot more, right? So it wasn't one person saying, this is a decisive moment. It was saying, well, I'm going to give you 10 minutes worth of this stuff. And I think there's a lot of useful information there about how to live in the world that you can only get either from video or from building a physical robot and having it roam around. So that's going to open up things a lot. How do you do it? Pretty much the same techniques as we have now. But the problem is that you get 60 frames a second or 30 frames a second, whatever your video rate is, as opposed to just one picture at a time. And so really we're constrained by the computing power. And some of it is we'll need better ideas for how to handle it. But I think mostly we're waiting for computers to get 100 times faster, and then we'll be able to process all the videos. And I hope we'll gain a lot from that.
In your presentation, you're talking about all these models which are mathematical, right? And as we build more complex models, we are moving into these higher dimension spaces. And my question is, if you're going to use models to verify models, where does this end? Like, what is the foolproof method to ensure that the model that I've built is learning correctly or is predicting correctly?
So there is no foolproof. You can measure it, and you measure it on a test set. And if it does well, that gives you some confidence. And if you want more confidence, you can do another test. And so I think one of the things that's really interesting here is that we've changed computer science from a mathematical science to an experimental science. So there's still a lot of math involved. You still have to understand the math. But it's becoming less a factor of, can I prove this is correct, to one of saying, well, I did this experiment, and now I'm going to analyze the result. I got 90% right. That's pretty good. Am I happy? Can I improve it some more? Let's worry about that. So I think it'll be a combination of that type of experimental analysis, just as, somebody published a paper of saying, here's a new treatment for this disease, and it was effective. Well, should everybody rush out now and do that treatment? No, probably not after just one paper, right? You probably want to wait and say, can we replicate this study? And if we replicate it a bunch of times, then we have more confidence in it. But in addition to the replication, we probably also want some theory behind it. So we want to say, this drug works, I tried it in 5 trials, it worked for everybody, and here's the biochemical reason why it works. Oh, and by the way, because I understand the processes, here's a subgroup of people who have these other things, and they probably shouldn't take the drug because it wouldn't work for them. So it's a combination of more experimentation and more theory that gives you more confidence, but you never get to the point of proving it correct. You just gain confidence.
Dr. Norvig, first of all, thank you for this absolutely fascinating presentation. I decided to take the microphone for 2 reasons. The second reason is that we're getting close to the end of the time. And the first and the more important reason is that I have a question. You mentioned that the power of these techniques essentially resides in the availability of a lot of data. And essentially, the more data you throw at it, the higher will be the effectiveness and the accuracy of the learning algorithms. Google has access to a plethora of data, and every moment the volume goes up. There are other organizations or corporations, Amazon, probably Facebook, I don't know, maybe Uber trying to collect a lot of data. Maybe the National Security Agency has a lot of data. Yeah. But given the power associated with machine learning and the kind of fascinating things that we can do with it in the future, are we entering a world where those who have access to data will have will not be on the same level as those who don't?
Yeah, so that's a great question. So first of all, there's computer access and power is growing for everybody. And so some of the things I showed, like the word sense disambiguation, you can get 97% running on my laptop. You don't even need an external hard drive. All the data you need and the processing power you need runs in a laptop. You can do a great job, right? So much more is open up now than was available 10 or 20 years ago to just an individual with a small amount of budget. Even more so if you have like a couple $1,000s, you buy some GPUs, you can do a great amount. There's a lot of things you can do on your own. It's also true that a big company is going to be able to do more. And I think what's going to happen is that the big companies will want to share that or rent that out. And we've already seen that in the case of computing power. So some of the companies you mentioned, Google, Amazon, Microsoft, all have a lot of data centers and are happy to rent that out to customers at pretty good rates. So you don't have to have the capital investment in buying all this computing. You just have to pay a small amount, say, I want to run this computation, I can get an answer. What we haven't seen yet, but I think will come, is sharing of that data, right? So we're just starting to get there. So Google, Microsoft, and others have APIs you can call. IBM is very big on this, where you can say, I want to recognize what's in an image. And so you pass in an image to a web service and you get back a labeling of what's in it. And you can do that both just using their model on its own and get back sort of generic labels, or you can add to that model by training with your own specific images. And now you have your own specific model and you can train against that, but that model was built on top of what was already there. And so I think companies will be happy to, they've invested in this resource, they'll be happy to make it available to customers rather than to try to hoard it. And the question will be, how do we work this all out? How do we share this data? How do you call in? And can we make it possible for people to donate data back? And if we do, what are the security issues and privacy issues around that? And that's all to be worked out. But I think we're more likely to see sharing rather than hoarding of data. Now, national security agencies probably don't go to them and ask to share their data, but the commercial providers, I think, will.
I was going to ask the audience to join me in thanking you for delivering an absolutely fascinating presentation. First of all, you did a great job of explaining a very complicated and advanced concept in extremely simple terms using beautiful imagery and graphics, and it made it easy for people who probably didn't know much about machine learning, and you made it useful for those people who are experts in the field. So terrific. It was just fascinating. I'm happy to announce that today we're starting a new thing at Stevens. I have the honor of presenting Dr. Norvig with the President's Medal, the first to be conferred at Stevens Institute of Technology. The medal is awarded for his significant impact on society, his contributions to science and technology research, and for his deep and widespread impact on business and education. Dr. Norvig has illuminated some of today's most critical topics, such as machine learning, which have been vital in informing the public's understanding of the influence of technology on society. As a further tribute to Dr. Norvig's significant influence, again for the first time, starting next fall, we will have a student at Stevens Institute of Technology that Dr. Norvig will have a lot of input in selecting, who will receive a scholarship in honor of Dr. Norvig. We decided that Dr. Norvig doesn't need another tie or another Stevens mug. So we figured by putting his name on the scholarship that a deserving, talented young man and woman will receive, he will have a much more profound impact. And he told me that because he has frequent visits to New York to meet with his colleagues at Google in New York, he might find the opportunity to come and actually visit the student. So without further ado, let me see if I can find your medal. It's a beautiful box. And our photographers have asked me to move a little closer to there.